My dear friends, this is Bhunesh Oza. We were talking about transformer, large transformer protection, but due to some reasons, I'm not being able to continue that. I think there should be at least 10 or 12 videos, out of which 3 we have completed. But we will complete that transformer protection also. But meanwhile, these presentations are ready. So I think I will present that, because in any case, we have to complete the full power system protection. So transmission line protection is important, and it is done in 3 ways: by overcurrent and earth fault relays, by distance relays, and line differential relays. Actually, overcurrent and earth fault relays we would have taken first, but it was put up in the module. So I did not take it. But then now we have completed distance first, and we have completed line differential also. And we are taking the first, rather, the poorest kind of protection, because there are many problems in overcurrent and earth fault relays. Distance protection is better, and line differential is the best for transmission line protection. But in any case, we have to learn overcurrent and earth fault relays, as we discussed last time, that 66 kV, 11 kV, and 6.6 kV lines are protected by overcurrent and earth fault relays only, because economically you cannot use distance protection because it is costly. The general rule is that you can spend 10% of 10% in protective equipment, 10% of the cost of the main equipment for protection you can use. So for 66 kV and below, you have to use overcurrent and earth fault relays. Not only that, but beyond 66 kV, 132 kV, 220 kV, 400 kV, 765 kV, whatever you tell, you have to use overcurrent and earth fault relays as backup. So the importance of overcurrent and earth fault relays cannot be denied. So in the first session, we have seen that a very primitive kind of radial feeder. And when I am saying primitive, because the interconnected system in the state is very complicated, and to set the relays is very difficult. Therefore, I am telling primitive. But such radial feeders are existing in today's protection world also, because 66 kV onwards, says from 66 to 11, 11 to 415 is a radial network. So radial network does exist, and we were discussing that radial network, right? And in that radial network, we have seen the detailed single line diagram. Now we are going to a diagram which is simplified, right? We had seen the simplified diagram also. We had removed transformers. And now our main problem is how relays will decide the location of the fault. Because we have to remove only the least faulted section from the remnant of the healthy power system network. So how will the relays decide? How will they discriminate? Right? So we have taken 3-section radial feeder, and in that 3-section radial feeder, R1, R2, R3 relays were there. I told you that R1 is not single relay. There are 4 relays, 3 for 3 phases and 1 for ground. That is for earth fault. So how do we discriminate for fault location? So we see first this the instantaneous overcurrent relays for radial feeder protection. See, if you use instantaneous, because you see they are very fast. So speed, that means we have to protect the equipment as fast as possible. So instantaneous means maximum 3 cycles. Nowadays in numerical relays, one cycle relays are also available. No doubt, one cycle relays were available in electromagnetic era also. The read relays were very fast. So instantaneous overcurrent relays we will be using. So those 3 relays R1, R2 and R3 in the radial network are instantaneous overcurrent relays. And what will be the discriminative quantity? Current will be the discriminative quantity, because IF, the fault current, is equal to E by Z. Z is the impedance of the line, total line, that is generator, transformer and line, because E is the generated EMF. So as the Z increases, current decreases. We use this decrease of current as a discriminative quantity. That means if the current is less, the fault is far from the relay, and if the current is high, then the fault is nearer the relay. Right? So what I do is, I make the relay R1 to reach up to B. Let us see whether we can see that figure. That figure once again somewhere. If we can see that figure, I will show you this figure. That what I am trying to tell. I am trying to tell this, that the relay reaches up to R1. Oh, I'm sorry. It seems in these slides that figure is missing. But in earlier class we had seen that that means a generator on one end, and there were 3 relays for first section, say R1, and for second section R2, and then third section R3. So this is what we are doing. So what we do, we make the relay R1 to reach up to bus B. Here generator bus is A, then bus B, then bus C, then bus D, and from D onwards there is a load. So pickup of setting of relay R1 is IF, fault current at B, divided by CT1 ratio, first CT ratio. So if I set the relay R1 will reach up to B, therefore it will protect section AB. Right? Similarly, R2 will reach up to C, and it will protect section BC, and R3 will protect section CD. That is what, that easily, I mean, we can discriminate between fault locations in different sections A, B, C and CD. But you see, friends, this simple, so simple looking protection is suffering from many disadvantages. And we are going to conclude that, therefore, instantaneous overcurrent relays alone cannot be used for transmission line protection. You can use them as a assisting feature, auxiliary feature. Part of the line can be protected by instantaneous relay, but not full line length. So what are the reasons? What are the problems that does not allow us to use the instantaneous overcurrent relays fully, only instantaneous overcurrent? First thing is unrealistic setting accuracy. For protective relays, accuracy is not important. Reliability is important. Reliability means relay must operate when it is called for to operate. That means when there is fault in the protected line, it must operate. And it must not operate when fault is outside its zone. That is reliability. Reliability is a qualitative term. It is not quantitative term. Accuracy is not that requirement. Accuracy up to 10% so often is allowed. But if we allow even 5%, then what happens? That I want to protect 100-kilometer long line, but relay is allowed to make a 5% error. Means it can protect 105 kilometer or 95 kilometer. Both possibilities are wrong. Because if it protects 95 kilometer, then who will protect remnant 5 kilometer? And if it protects 105 kilometer, then in the next section relay R2 is there. That will also operate and R1 will also operate. So both sections AB and BC will trip. So load from B will also be cut off unnecessarily. Healthy lines will be cut off. That is the main problem. Unrealistic setting accuracy. Relay accuracy is giving me a problem. Fault just at the end of the line section and for fault just after the line section cannot be differentiated by this unit system of protection. Unit system is relays sitting at one end and it is protecting the whole line. Right? That is one very important disadvantage. Second very important disadvantage is this method does not give backup. Relay R1 is reaching only up to B. Beyond B it does not reach. That means if R2 fails, R1 is not going to give backup. It is a very big disadvantage. Backup is a must because relay can fail. Nobody can tell that. Not only relay, it's not a question of relay. Relay may operate, but breaker may not operate. Relay and breaker both are good, but CT is not good. CT is not transforming properly. You see, CT, relay and breaker, anything fails, then you are gone. That means you are not protecting. So backup in relaying is a must. You must be ready for at least second line of defense. For very important equipment like generators, we go up to 4 lines of defenses. You see, but at least for transmission line, you should go for at least 2 lines of defense. First primary and second backup, or first main and secondary. Main and secondary and primary backup, whatever you call it. Right? So it does not give backup. That is the second disadvantage. The third disadvantage before we talk about is ZS by ZL ratio. So we will have to define the terms. ZS is source impedance. Impedance from source to relaying point. Refer this next figure. ZS. Right? Source from source to relaying point. Say for R1 it is ZS1. It is not written here, but it is ZS1. And ZL means from relay to fault. Now maximum ZL can be AB, line AB full, because R1 has to protect up to AB. But here you see ZS is very small and ZL is large. Therefore ZS by ZL ratio is small. So it does not create any problem. But if ZS by ZL ratio is very large, right? If I'm talking of a last line, third line, I don't know whether it's given or not. It's not given. But if we are talking about the third line in the figure, we have seen AB, BC, and CD. So CD is the third line, and R3 is the relay. So for R3, the ZS is from generation up to R3. So line AB is also considered in ZS, line BC is also considered in ZS. So ZS is very large. And ZL is just CD, 40-kilometer long line. So if you consider ZS, ZL very small with reference to ZS, then fault current is IF by ZS, which is constant. So your inverseness in characteristic has no use. Inverseness is not justified. That is the problem. So instantaneous overcurrent relays are highly prone to ZS by ZL ratio, and therefore they are they are they cannot be used alone, right? So that is the third problem. The fourth problem is that we have already discussed that the fault current is asymmetric, right? In first few cycles means up to about 30 to 50 cycles, depending upon ZS by depending upon X by R ratio. Your wave shape of current is asymmetric with reference to timeline. Then it becomes symmetric. Now, whether you will set the relay for asymmetric current or symmetric current, that is also a problem, because current is not always asymmetric. Current is asymmetric if if the fault occurs when voltage is passing through zero, but it is badly asymmetric. But if the current is passing through, if the fault occurs when voltage is passing through maximum, then there is no asymmetry at all. Current is fully symmetric. So, but you do not know when the fault occurs, when the lightning will fall on, will it fall, seeing the wave shape? You see, will the switching surge come according to a requirement? No. So you have to be ready for the worst case, that is fault occurring at voltage zero. That is maximum asymmetry. That is peak to peak. Peak to peak is 2.8, my dear friends. Because RMS to peak is 1.4 times and peak to peak is 1.4 divided by 2.8 times. So relay sees 2.8 times the current. If you allow 3 cycles to go, so at least it will see 2.5 or 2.4 times the current. Now you have set for symmetric value and you have to set for symmetric. So you are setting for symmetric, but relay is seeing 2.5 or 2.4 times the symmetric value. So it sees at least twice or 2.5 times the current. 2.5 times the current means what? Relay feels that the fault is nearer, because more current means nearer. Fault has occurred in second section and relay feels that fault has occurred in first section. This is known as transient overreach. Why transient? Because this is going to die down after 30 cycles. So time delayed relays are not affected by this transient offset. Only instantaneous overcurrent relays are affected. So you cannot set full line by instantaneous overcurrent relays. Usually it is assumed that 20% asymmetry will be there. So you have to set the relays for 80% of the line. That means instantaneous relay will protect only 80% of the line. Remnant 20% you have to think about. So that is transient overreach is a very big problem for instantaneous overcurrent relays. The next problem is that no doubt this instantaneous overcurrent relays, as we are talking, 20% as I told you, but 20% if you don't want to assume, and if relay manufacturer gives you as to what is his overreach, so often relay manufacturers are giving a percentage overreach of instantaneous overcurrent relay. Then the formula is 100B upon 100 minus A. B is equal to magnitude of 3-phase RMS fault current at the end of the feeder. Say if I am talking of relay R1, then I have to find out the fault current at B. 3-phase fault current at B, right? And that I have to convert into CT ratio, that is secondary side. So that secondary fault current is B and A is percentage overreach. So setting of I set instantaneous unit formula is 100B, 100 into B upon 100 minus A. This is how you can calculate the setting of instantaneous asset. It will not protect full length of the line, right? So this is what is proved for figure 7.2, which we had seen in the last slide. In the first session, we had seen if the ratio is 500/1 and the current is 5000 ampere, then the current becomes 10 ampere. So 100 into 10 divided by 100 minus 10, so 11.11. So it is 1111% of 1 ampere. And because usually the setting range for instantaneous overcurrent relays is 400 to 2000% in steps of 50%, you can set 1150. You have to go ahead. You see, you cannot go less, because if you go less, you are going towards bus B. So you have to go towards bus A. That means you will set the relay instantaneous overcurrent 1150 percentage of 1 ampere or 1150 percentage of relay rating. This is what you will do. No doubt, the static and numerical relays have given the solution to this. Say if your current is what? I is equal to Im sin omega t plus theta minus phi. That is sinusoidal current. That is steady state current. We are not worried about it. But our culprit is this sin phi minus theta e raised to minus RT by L. If this becomes 0, that means if phi is equal to theta, usually phi is 90 degree. Because you see, when fault occurs, our system is maximum uh, uh, inductive. Therefore, phi is equal to 90 degree. So if fault occurs at voltage maximum, so theta is 90, phi is also 90, so sin 0. So that is gone. Right. So we are worried about that DC offset. Sin phi minus theta e raised to minus RT by L. We have talked about that it is DC offset. It is not DC, it is sinusoidally decaying. I mean, it is exponentially e raised to minus RT by L, but it is decaying after 30 cycles and relay operates within a cycle or two. So you can consider it DC. So if you differentiate this DC will go, or at least it will attenuate. It will minus R by L sin phi minus theta e raised to minus RT by L. Sine component will be omega cos omega t plus theta minus phi, where omega is constant. I am not worried about it. Cos, I am not worried about it. Cos wave is just 90 degree phase shifted. I am not worried about it. I am worried about sine phi minus theta, which is attenuated by R by. I am saying attenuated because in our power system L is very large with reference to R. So if you differentiate, I am mathematically telling. Electrically use operational amplifier if it's a static relay, and in numerical relay it is yet easier. It is taking sample at every 1 millisecond. So di by dt is what? I2 minus I1. First sample minus second sample upon delta t. That is the time interval, 1 millisecond. That gives me di by dt. So I need only 2 samples and I will find out di by dt. So di by dt attenuates the DC offset. If L is 10 times R, then my R by L is 10%, then my attenuation becomes 10%. That means if the relay is overreaching by 20%, now it will overreach only by 2%. And if I double differentiate, then it will overreach by only 0.2%. So solutions are there in numerical world, right? But in electromagnetic world, there were no solutions. So that is one thing. The other problem is we are not considering the thermal withstand capacity of the equipment. Fault occurs, that is all right. 100 ampere is the rated current of transformer on primary side. Say fault current is 500 ampere. So 5 times the current is flowing. But 5 times the current transformer is capable to withstand up to say 15 seconds or 10 seconds. So you should wait up to 8 seconds. You should leave 20% margin. You should wait up to 8 seconds. You are not waiting. You are tripping within 1 cycle or 3 cycles. So you are not exploiting the thermal withstand capability of the equipment to be protected. That is the biggest disadvantage. That is very great disadvantage of instantaneous overcurrent relay. Also, when the fault occurs, the generators are going out of step, but generators can remain in asynchronous conditions for few cycles, 8 cycles, 10 cycles, 12 cycles. That depends upon the so to say the the but what should I say? The generator has its own uh, uh, its inertia. That means the time for which generator can remain in a synchronous condition depends upon its inertia constant. It can remain in asynchronous conditions for say 12 cycles, but you are tripping in 3 cycles. You are not waiting for generator. You are not exploiting the capacity of the generator to work in asynchronous conditions. So that also you are not doing. And last, very important, we are telling that R1 will reach up to B, but then for which fault? For triple line fault, I triple L is E upon ZL. And for double line fault, it is root 3 upon Z1 plus Z2. So root 3 upon 2 Z1, because for transmission line Z1 and Z2, positive and negative sequence impedances are same. So it is 0.866. That is, double line current is less. So will you make it to reach for double line fault or triple line fault? You cannot do anything, because if you make it to reach for triple line fault, then for double line fault, it will not reach there. It will underreach, right? Because it will reach for part of the line. And if you set for double line fault, then it will not reach for triple line fault. Right? So for triple line fault, it will overreach. So you can neither set for triple line fault nor for double line fault. LG I am not talking, because line to ground fault, the relaying philosophy is different, and that we will talk afterwards. But right now, we are concluding that instantaneous overcurrent relays alone cannot be used for protection. You have to use time delayed relays. Instantaneous overcurrent relays can be used in conjunction with time delayed overcurrent relays, but the instantaneous overcurrent relay will protect only 80% of the line section for triple line fault at that point with maximum generation. Right? Otherwise, you will be tripping unnecessarily a healthy section. So, with that conclusion, that the instantaneous overcurrent relays alone are useless, probably we end our talk because we will have to use another discriminating quantity. Current alone is not useful. So which another quantity we will use, that we will see in the third session. We will keep everything in suspense, because you see, you are saying the TV serials. So they end the serial at a point where uh, you are in suspense. You'd like to go to see for next week. So next week you are always ready, and they are selling. That is their marketing point. So I also become by now, because I've started, my sons have started business and helping them. So partially I have become businessman. I was a simple teacher, but now I have started becoming businessman. So I end up here with the uh, exclamation, with the uh, with the with that kind of uh, I will keep you in doubt what will be the next thing, right? What will be the next quantity that we will see. And so stay tuned with Adapt Me. Remain with Adapt Me. Let Adapt Me rise. Let Adapt Me reach to billions and trillions of people. So please share this video to as many people as possible. We'll be having some 15 videos on transmission line protection, and then we will again resume to transformer, then induction motor, then bus zone, then CTPT, circuit breakers, everything we are going to take. We would want to learn fully the protection in industrial pattern, not in the institutional pattern. Right? Institutes are teaching for examination. Teachers are reading books and teaching. Most of the teachers do not have any industrial experience. I have worked in power plant. I have done engineering of power plant, and with the industrial experience, I am teaching. I have read many books also. I have written also books. So with that experience, you are getting knowledge from an expert free of cost. So let that knowledge spread all throughout the world, in each corner of the world. Every engineer who is interested in power system protection should have seen and heard this video, right? So let me earn more and more view hours. With that, I thank you, friends, for patiently hearing me, and good day to everybody.